calculus is one of the courses for you at this semester. And calculus, we have heard of this several times from SSS till now. Calculus is not any big word. Calculus in short means calculation. And it was established by Newton and Leibniz in the 17th century. There are two parts of calculus, as you might have heard it from the SS level. We have differential calculus and integral calculus. There are two parts. Differential calculus, and then we have integral calculus. This course will take into consideration both integral and differential calculus. We are going to concentrate on differential calculus, then when we finish, we come with the integral calculus. Differential calculus talks about slopes of functions, the rate at which functions changes. But integral calculus talks about area of functions. And some will say that integration is the reverse of what differentiation is. One of the definitions of integration. But for now, we will say that differential calculus is about slope of functions, whereas integral calculus is about area of functions. And before a function can be integrated or differentiated at a particular point, the limit at that point must exist. And the function must also be continuous at that particular point. So before we start with differentiation, we are going to consider limits of functions. And we have limits of functions of several variables, but our concentration will be limit of functions of one variable, single variable functions. So we are not going to concentrate on several variables, but our lesson will be on single variable function. What we are trying to say is that if you have f of x equal to, say, 3x, if this function is graphed, we may see something like this. This is y equal to 3x. What we are saying is that as s approaches a value here, say 2, this function will also be approaching a value. That is, when you put in 2 into 3, it will give a value, into 3s, it will give a value of 6. So the function will be approaching 6. So you can approach these two either from this side or you approach from the other side. And we are going to find out what will happen if values try to approach 2 from 0 and also approaches these two from a value bigger than 2. We are going to see what will happen. So we want to complete this simple table. This is x, this is f of x. And don't forget, our f of x is 3x. F of x is 3x. So we are going to choose values closer to 2. x is 1.9. We all know that 1.9 is not up to 2. So when you put 1.9 into 3x, that is, we are going to write f of 1.9, which is 3 times 1.9. And when you compute into your calculator, you come out with 5.7. We can also increase the value of x to 1.99. That is, we are heading towards 2. From 1.9 to 1.99. Do the same thing. Find the functional value of x, which is 1.99. When you put 1.99 into the function, you will produce 5.97. Again, if you put 1.999 into the function, the functional value will be 5.997. If we increase further, 1.9999, then the value also increase to 5.9997. And when x is 2, we said the value is what? 6. We also want to approach this same value 2 from a different level, the values bigger than 2. An example is 2.1. When you pick 2.1 into the function, when x is 2.1, what will happen? We have 6.3. That is, when you put 2.1 into the function, you get 6.3. Similarly, if you try to get a smaller value than this, maybe 2.01 into the function, it will give you 6.03. Again, when you put in 2.001, then the value will be 6.003. If you reduce further towards 2.0001, then the value will also be 6.0003. So when you check closely, as you approach 2 from bigger values greater than 2, as you approach 2 from 2.1 towards 2.00, as values reduces towards 0, the functional value also begins to reduce from 6.3 to 6.03 towards 6.003. Similarly, if you reduce x, if you increase x from 1.9 to 1.99, the functional value also increases from 5.7 to 5.97. As you begin to increase, the functional value also increases towards the 6. So in short, what we say is that as the smaller values increase, we say the limit as x reduces or as x approaches 2, the functional value of 3x is equal to 6. It depends which way you want to approach. Don't forget, 2.001 is to the left of 2. So from 2.1, we are moving towards 2 from the right. But from 1.9 towards 2, we are also moving towards 2 from the left. So we have two-way limit. You can say limit as s approaches 2 from the left of the function or limb as approaches to from the right of the function, and they must always give you the same answer. Either you approach from the left, that is always negative sign on top of the value, or you approach from the right, which is a positive sign on top of the two. Sometimes we don't write, and if it is not written, then we say it is approaching from the right. That is the assumption. But if it is written, then it is approaching from the left. If it is written negatively, so but please, this negative on top of 2 doesn't mean the 2 is negative. It tells you the direction where the values approaches from. If it is from the left, you see negative. If it is from the right, you see positive on top of it. Good. So, in short, what we are saying is that if you have a function and the function is f of x, I want to find the limit. By definition, we say that lim as s approaches a of the function is always equal to f. And I said, from the numerical values we use, the functional value is always equal to limit as s approaches a from the right of the function, and the answer is always L. So you can approach a function from either left or right, and you must get the same value. Theorem. If f of x equal to k, then limit as s approaches a of f of x is k. Theorem 1. If f of x, that is, if the function is k, where k is constant, then the limit as s approaches a of f of x is always k. That is, limit of a constant is the same constant. Example. If f of s equal to 4, lim as s approaches 2 of 4, the answer is 4. It doesn't change. So limit of a constant is always the constant. Good. Let's move on to second theorem, theorem 2. Theorem 2. If limit as s approaches 2 of f of x limit as s approaches a of f of x plus g of x is always equal to limit as s approaches a of f of x plus lim s approaches a of g of x. What it means is that if two functions are being added, and you want to have a limit of the two polynomial functions, or two polynomial functions, you pick the limit of the first function plus the limit of the second function. So assuming if lim as s approaches a of f of x is equal to L, and limit as s approaches a of g of x is also m, then what we are saying is that lim as s approaches a of f of x plus g of x is equal to L plus m. Example. E.g., this is a quadratic function, and the functions are being added. So to get a limit, per the theorem, you have limit s as s approaches 1 of 3x squared plus lim as s approaches 1 of 2x. And don't forget, x is not 1 but approaching 1. So as s approaches 1, this function also approaches 3 plus, and as s approaches 1 here, the 2x also approach 2, and the answer is 5. Good. You may try this as an exercise. Limit as s approaches 3 of 2x squared plus 4x. Limit as s approaches -1 of 6x cubed minus 4x plus 3. We want to consider the next theorem. That will be theorem 3. What theorem 3 says is that if you have limits as s approaches a of function f of x multiplied by g of x, then it's going to be lim as s approaches a of f of x times lim as s approaches a g of x. What it means is that if two functions are being multiplied and you want to take the limit as the variable approaches a certain number, say a, then it's the same as taking the limit of the first function, put the answer down, find the limit of the second function, then you multiply the results as the final answer. For example, we are to evaluate as S approaches 2 of 2x squared plus 3 against 4x cubed plus 5. So per this theorem, we have to pick the limit of the first function, then we multiply the result to the limit of the second function. And each of them too is a polynomial function. Please, you can expand. If you think you don't know the theorem and you want to find the limit of this, you can also expand and find the result, the limit of the results, which will be more tedious. So it's advisable you use the theorem. So solution to this problem. Per the theorem, we are going to write limit as s approaches 2 of the first function, 2x squared plus 3. Then we multiply the result to the limit as s approaches 2 of the second function, s cubed plus 5. And per the second theorem, we pick limits individually, limit term by term. So limit as s approaches 2 of the first function, 2s squared, plus limit as s approaches 2 of 3. Then this result will be multiplied by lim as s approaches 2, 4x cubed plus lim s approaches 2 of 5. It implies that we are going, as s approaches 2, the first function approaches 4 times 2, which is 8, plus the value here will also be, as a limit of a constant is 3, times, as s approaches 2, we have what? 2 cubed, which is 8. 8 multiplied by 4, the answer is 32. Plus, limit of a constant is constant, so the answer is, there is 5. So what is happening here is 11. We multiply by this times that plus that will be 37. And 37 times 11, the answer will be 407, sorry. Now we want to continue our discussions on limit, and we want to consider theory 3. Theory 4 rather, we have already done 3. Per this theory, what it says is that if you have lim as s approaches a of f of x divided by g of x, the theorem says that the answer is the same as limit as s approaches a of f of x divided by limit as s approaches a of g of x. What it means is that if you have a rational function, you find the limit of the numerator, the result is divided by the limit of the denominator, provided provided g of a is not equal to 0. or both g of a is not 0 and f of a is also not 0. If both are 0, it will be 0 over 0 and it will be indeterminate. But if only g of x is 0, g of a becomes 0, then it tells you that you will get something divided by 0 and it is undefined. So anytime you are given such a rule and you want to apply it, make sure you test for these conditions before you apply. Example 1. E.g., we have limit as x approaches -1, x squared minus 1 over x plus 1. And per the rule, as x approaches 1, the numerator will be 0, -1, the numerator will be 0, the denominator will also be 0, so indeterminate. So before you can apply the rule, you can apply our algebra, simplify, factorize the numerator and see whether you can get a linear factor to cancel that of the denominator. So we have limit, s is approaching -1. The numerator is difference of 2 squares, so it has factors x minus 1, x plus 1, and x plus 1. Then common factors will cancel out. In that case, x plus 1 will cancel x plus 1, we have limit. As x approaches -1, x minus 1. And as s approaches -1, the result is -1 minus 1, and the answer is -2. Please, as you simplify the function, don't forget to keep the limit. If you don't bring the limit, you'll be penalized. So always keep the limit until you evaluate the limit. So after you have evaluated the limit, you forget about it and then you get the answer. Good. Let's try another example and see. Good. Our example 2 is also like this. Limit as s approaches 2, s squared minus 4 all over x minus 2. As s approaches 2, if you try to put in, as the theorem says, the numerator will be 0, denominator will also be 0. In that case, we try to simplify. Let's look for linear factors of the numerator. It will be limit as s approaches 2, we have x minus 2, x plus 2, which is difference of 2 squares. And the denominator will be x minus 2. It has a common factor, denominator to cancel 1 here, and the result will change to limit x approaches 2, we have x plus 2. And as s approaches 2, the answer is now 2 plus 2, which is 4. We want to also consider another example. We have limit as s approaches 9. The function is 9 minus x here. Then we also have 3 minus root x. And when you check well, as s approaches 9, numerator will be 0. The denominator too will be root 9. And root 9 here will be 0. 3 minus 3, that one will be 0. So you have to simplify. But this one, since this one is said, we apply your knowledge in sets at the SHS where you were trying to do what we call rationalization. So to rationalize the denominator, you look for the conjugate of the denominator, then you multiply both numerator and denominator by the conjugate. So let's try to the limit as s approaches 9. The numerator is 9 minus x divided by 3 minus root x multiplied by the conjugate 3 plus root x divided by 3 plus root x. And when you check the numerator will be maintained, we have limit as s approaches 9. The numerator is now 9 minus x times 3 plus root x. But that of the denominator will be difference of 2 squares. So it will be 9 minus, when you square the second term, it will be x. So these two factors will cancel, and the result here will be limit as s approaches 9, 3 plus root x. And as s approaches 9, root of 9 is 3. So the answer is now 3 plus 3, which is 6. Good. When you get the lecture notes, you will get several exercises for you to try your hands on. Thank you.